Good evening. Thank you very much for attending. Welcome to our class for 2601. So today we're going to be discussing properties of regular languages. So if you've missed the past few classes, we've been dealing with that Lynch theorem. So we're done with it. We're going to do properties of connected languages and decidability today. So this will then mean that our last class is going to be on Wednesday, and we'll wait for revision on Thursday while we wait for revision classes. So on Thursday, we're going to be doing pumping learning. So during this period, from Thursday to end of the month when we start our revision classes, just make time to go through all the videos that we have done, attempt all the past exam papers that you can, and then by all means send them to me. So that I can review them. So the email is still the same, kudaita@tutor.com, and I will be there to assist. So please do attempt some questions. Please do master a few concepts. Where you struggle, then come back to me. Right. So I think that's where we'll make a whole lot better for all of us. Now, today we are going to be talking about properties of regular languages, right? And to do so, we're going to be aided by the slide. So, right. We have got a couple of properties that we are going to look at, but the simple ones, we see that look at the properties for union, the properties for product, and the properties for clean closure, right? So we can say that number one, right, if we're looking at this, it says if L1 and L2 are regular languages, then L1 and L2 or L2, L1, L2 and L1 clean closure are also regular languages. So what this means, in other words, it can be interpreted to say the following. It would mean to say regular languages are closed under union, closed under product, and closed under clean star. Right. So sometimes they can ask the question to say regular languages are closed under union. What does that mean? So the response is going to be it means that if L1 and L2 are regular languages, then L1 or L2 are also regular languages. Right. Or if you're talking about product, then we include product. If you're talking about clean star, we include clean star. So that is the meaning of closed under union, closed under product, and closed under clean star. Right. So that is the first theorem. We say that if we are given two regular languages, their product and their union is also a regular language, and the clean star of a regular language is also a regular language. Right. Now, if we are given that L is a regular language, right, then the complement is also a regular language. So the complement is also a regular language. So if you look at this, let me just move one step back. This has been justified by clean star, right, or the clean theorem. So in clean theorem, we had the discussion and said if you are given a finite automata for one, a finite automata for two, we managed to generate the finite automata for the third one, right? So we can use that same proof to show that or to give the new FA for L1 or L2, L1, L2 or L1 clean star. So if you go through the previous three videos, you will see that you are able to do exactly that. All right, now, here we're saying that if L is a regular language, then L complement is also a regular language. In other words, the set of regular language is closed under complementation. So what does this mean for us? It means if we have got a finite automata, and we've got say A that accepts A and then followed by B, it accepts the word AB, and then anything. Then here say we can have A is followed by B's, right? So if it accepts words such as A is followed by B, so B goes to A, looping states with an A or a B. So initial states, we've got an A and a B. This we've got an A and a B. Here we've got an A and a B. So perfect, right? So now, if we say that this is L, right? Then L complement, right? What do we do to get L complement? all final states, this is L complement, all final states, this to become final states, this to become final states, to become final states, become final states, and as well, right, all non-final states become final states. All non-final states become final states. Become final states. Okay. So if we have these two, so that is how we convert from L to L complement. So in this case, right, we had number, if I'm to number them, I have 1, 2, 3, and 4. Number 4 was a final state. So in the complement of this language says, this is now, or we can say this is now these are now the final states that we have. We now have that, and that. All the non-final states become a final state. All those that were not final state or were final states no longer become final states. So that is how we show the complement of a regular language. Right. What was final ceases to become final, and what was not final becomes final. Right. Now, let's look at the next rule. Right, so theorem 12 says if L1 and L2 are regular languages, then L1 intersection L2 are also regular languages. In other words, the set of regular languages is closed under intersection. Right, so to prove this, right, we'll use this Demoves theorem. It says that L1 intersection L2, it says that it is equivalent to saying L1 complement union L2 complement, and then complement. So this we can write, it becomes L1 complement or L2 complement or L2 complement and the complement of that. So this is equivalent to saying L1 and L2, and to say it's equivalent to say L1 intersection L2, and that the union of the complements complemented is also the same as the intersection. Right. Now, we'll see a little bit later on how that comes out, right? We'll see a little bit on later on how that comes out. So this is, if we can write it like this, it means that we know how to give L complement, we know how to give L complement, and we know how to find the union of two finite automata, and we know how to give the complement of that. So it is very possible for us to find the intersection of the two languages. Then the next one, right? So a couple of questions on head. So this is from previous assignments. So you need to attempt the assignment questions. Then closer to the data, also send the attempted solutions via email. So in the meantime, just go and try and do them, and then see what you can get. You can send it to me for correction as well. So it says, which one of the following statements about regular languages is not true? Right. They say if L1 and L2 are regular languages, then L1, L2 is also a regular language. That is true. Okay. So this is true. Then if L is a regular language, then L complement is also a regular language. True. If L1 and L2 are regular languages, then L1 intersection L2 is also a regular language. True. L1 intersection L2 is equivalent to L1 complement intersection L2 complement, and the complement of that. So this is false because the actual one is L1 complement union L2 complement, complement, like that. Right. So that is how that goes down. Then question 6 says, given the finite automata representing L below, which one of the following is the FA that represents L complement? So the FA that represents L complement is going to have, we're going to make this a non-final state and make this a non-final state, and this becomes final state. We don't have the options, but the option that would have had this option, correct this one, they will be correct one. Right. The next, we can say which one of the following statements about non-regular languages is not true. So which one of the following statements about non-regular languages? So we are yet to do non-regular languages at this point, so we are not going to touch this. But we can attempt with the knowledge that we have now. So which one of the following statements about non-regular languages is false? So they're saying it's false. So we've got too many negations here. So we're saying which one of the following about non-regular languages is false, or which one of the following is false. Okay. So they say there exists a finite automata that accepts a non-regular language, right? So this is false, right? You do not have that. Okay, cool. So we're going to look at this question more or less after we've done our pumping level. So let us skip this for now. Right. We are given the finite automata. Right, we're also going to come back to this question. We just need to cover topic decidability. Okay. So that's it for the properties of context-free. Sorry, of regular languages. That's it for the properties of regular languages. So regular language and context-free language. After we've done regular languages, realize that in COS2701 we're going to be doing context-free languages. So I'm switching between the two because I was also doing context-free languages for them. Right. Decidability is a concept where we are asking the question, is there a solution to this? If there is a solution, what is the procedure to get the solution? And so in decidability, we ask, or for regular languages, we can ask the following questions. How can we tell whether two regular expressions define the same language? How can we tell whether two finite automata accept the same language? How can we tell whether the language defined by a finite automata is finite or infinite? Can we tell whether or not a finite automata accepts any word or is empty? Or is the language accept any word or is empty? So we ask ourselves these questions about these languages and say, will this language help at all? Does it bring any help? Is it going to accept any language? Right? Is there a way to check whether or not it accepts some way? So those are the questions that we have is decidable regarding finite automata. Right. So let's look at decidability. Right. We said a problem is decidable if it has got a decision procedure. And a decision procedure is an effective solution to a problem that is a yes or no answer, a binary answer, a Boolean answer. Right? Why Boolean? You see the importance of Boolean in the sense that our computers operate on 0 to 1 basis. So that is equivalent to true or false, yes or no. So as long as you've got a Boolean response, right, and you've got a solution that leads to a Boolean response, then we call that a decision procedure. So in short, a decision procedure is a solution leading to a Boolean answer, or is a procedure leading to a Boolean solution. So if we have got a decision procedure for a problem, then we say it is decidable. So we want to find out of the questions that we just asked, which ones are decidable. Right. So firstly, it says there's an effective procedure to decide whether a given finite automata accepts any words, two finite automatas are equivalent, and whether two regular expressions are equivalent. Right. So we've got decision procedures for that. Now, let's check this one. It says, can we accept a language? Can we accept a word from this language? So there are two ways we can check whether or not a language accepts a word. One, using the regular expression, and two, using the finite automata. Right? So the first one says, if we're using this, right, we say, number one, we remove all clean closures, remove all clean stars, all clean stars. Okay. Then number two, after we remove all clean stars, so what's gonna remain in regards to this question? We're gonna have A or now, A B or B A. Then we're going to have now or B, like that. This is what's going to remain. Then number two, if for any union, right, we need to discard the right hand side of the union. Discard right hand side of union. Right, so what do we mean? We're saying we're going to lose all these. We're going to throw them away. So number three, we're going to be left with A, B, and now. Right. So that is what we're going to remain with. And then we say 3, if at the end we have a word, then L is not empty, or we can say it accepts some weight. Right. So this specific regular expression accepts some weight. So usually, it makes sense to say that if there is a regular expression, it's going to accept at least some weight. Now, the second method would be to say, examine the finite automata to see whether or not there is any path from initial to the final state. If there's any path, then the machine must accept some weight. For one, the word that is a concatenation of the labels of the age from just initial to final. So that is how we go about it. So the procedure is as follows: paint the start state blue. So if you're given a finite automata, paint the start state, it's going to be painted blue, right? Then from every blue state, follow each edge that leads out of it. So you follow an edge that leads out of it and paint the destination blue. So if you're getting here, then you paint this blue. It also says then delete this edge. So you then delete this edge that you followed. Right. So that is step number 2. Then number 3, repeat step 2 until no new state is painted blue. Then stop. And then number 4, when the procedure has stopped, if any of the final states are painted blue, then the machine accepts some weight. If it does not, or if not, then it does not accept any weight. So the prerequisite for you to accept a weight, you need to have a path from initial state to final state. Right? So that is the procedure for that. Now let's test, does this one accept any weight? Right? Does this finite automata accept any weight? So we're going to start and say, let's have initial state is painted blue. Let's paint it blue. Right? Then if the initial state is painted blue, so let's paint it blue. Right. So they say follow the outgoing transitions. So we're going to have this and that. So we're going to have these ones painted blue, and these transition leading to it deleted. Right. So so this one is still going to be A or B. Right. Then we can follow all the outgoing transitions as well. So from this one, we follow the outgoing transition. It takes us to okay. So this was the second part. So let me put it like that. Then we also have that. Then we also have then we also have B, A, B positive, A or B. So these are supposed to be initial states. So this is what we end up with. Right. Then next we can then say from this state we paint wherever it goes. So we now have the initial. This was supposed to have been painted blue. This is painted blue. So we've got the initial that and that which are already painted blue, right? So these are already painted blue. We want to follow and see which other ones will be painted blue. So this goes with an A, you go here, right? With an A, you go to the state. So this is going to be painted blue, and we're going to paint blue, and these two going to have them. Transition coming back, pick red, transition coming back over there within AB. Okay, and then this guy is never going to be painted blue because there won't be anything getting to it like that. So we're still gonna have it in A or B. Right. So this is a possible solution. Right. So what could possibly end up happening is the following. So this is the first instance without wasting any more moves that you can get to blue. But what can end up happening is if you carry on with more steps, you are going to result in this disappearing as well, this transition and this transition disappearing as well. So, but in the very first instance, you can stop here. All right. Any questions? Sweet. Now, let's look at another one. Let F be a finite automata with n states. If F accepts any words at all, then it accepts some words with n or fewer letters. Right? If n accepts any words at all, then it accepts words with n or fewer letters. So say, for example, I'm just going to demonstrate with an example to say, right, a finite automata that accepts one word, right, or a finite automata that accepts with two states will accept one word. So 2 minus 1 or fewer one word, right? A finite automata that accepts now is going to have one state. Right? If it accepts now, it's going to have one state. So we're going to have either one letter words or fewer. So that's what we're saying. So the proof says the shortest path from initial to final, if there is any, cannot contain a second, because if we go from initial to state, so there was one that they were referring to, right? So they're saying we cannot, the shortest path cannot contain a second. Right? So the only time that we're going to have a letter or a word more than the number of states is when we've got a loop. So a loop is the only one that we've got, or a second is the one that we have determined that we've got more than. But since we can take the shortest word without going through a loop, then it means the number of letters are going to be n or fewer. Right. Then let's look at this one where we want to check whether or not two given finite automata are accept the same words or not. Right. So here they say using the method of intersecting each machine with the complement of the other proves that these two finite automata do not accept a language. So they say if you build this for two finite automata, if you build this and it contains, right, you've got an element, you've got something else is an element of that, right? If you have got an element that is accepted in this one, it means that your given finite automata are not equal, right? Or X is an element of that implies FA1 is not equal to FA2. Right? But if no element, right? So if we have got all X and we know that no element, so we've done some logic. So we're saying all X, for all X, X is not an element of that. If no element belongs to this set, it means that FA1 is equals to FA2. Right, so let's use that proof by means of set. Let's prove that using set. So let's say we have got, so we want to prove L1 intersection L2 complement, or L1 complement intersection L2. Right. So if we've got two L1, L2, L1 intersection L2, so we're going to put them in a universal set. Okay. So if we've got L1 intersection L2 complement, so this is all L1, and we want to intersect L2 complement. The complement of L2 is going to be everything. L1 intersect L2 complement. So L1 is this guy. L2 complement is everything that is outside. So they intersect in such a way that we have got, or we want the common ground. So what's common to that is L1, right? This part that does not belong L1, and then it intersects with L2 complement. L2 complement will include everything, including this part. So where they intersect, what's common is going to be that. Okay. Then we are going to have also, we can go now and say, so this is L1 intersects L2 complement. So here we can then further have L1, L2. We want to have L1 complement intersects L2, which means we're going to have that. Okay, and then the union of that says, the union of this says, the union of this says 1, 2. If we take the union, we're just gonna add this one and that one. Right. So if what we're saying is the union of this is this and that, right? So you find that the intersection is empty. The intersection is empty. If the two languages are the same, all the elements should be residing on the intersection. All the elements should be sitting on the intersection. So if this guy is empty, right, or if they are equal, we should have nothing sitting here. We should have nothing sitting there. Everything should be inside here. So if you have anything remaining, then they are not equal. If they were equal, all these will be empty, and the intersection will be the one that will be full of the elements. Right. So we say if this accepts any element, then we say they are not equal. If it is empty, we say they are equal. Right, now if you're given a finite automata, how then do we end up drawing or how do we end up attempting such equation? So to attempt such equation, we need you to use the following. We know that we're saying L1 complements L1 intersection L2 complement, or L1 complement intersect L2 is equivalent to say, so we say intersection says, so it becomes L1 complement or L2 complement or L1 or L2 complement and complement. So L1 or L2 complement the complement of that. So if we do that, then you see that we can then apply Kleen's theorem to this, to say I'll find the complement. To find the complement here, we're just going to negate that. So this question I'm not actually going to do, right? It's take a bit long. So what they ask in the exam, or is to say this, right? What I would rather do is I will include this as additional resources on the portal. I'll send it as additional resource, the solution to this question, right? So, because step by step, you find the complement of this, you find the complement of that, and then you find the union of the complement of one with the other. Then you find the union of the complement of the one with the other. You complement them, then you find the union of the two. So the steps involved there, if you've been following Kleen's theorem, you see that to find the union of the two is a process on its own, and then we are going to find 1, 2, 3 unions. So that solution will be sent separately. So again, if you are looking for examples, you can go and find them in the study guide. I remember there were some examples that are in there as well. But the theory behind it is to say, if this guy accepts an element, then they are not equal. Otherwise, if they do not accept an element, then they are equal. Right. Let's then come back to this decidable one and say, let F be a finite automata with n states. If it is a finite automata with n states, then if F accepts an input string W such that the length of the word W is between n, which is the number of states, and less than 2n, then F accepts an infinite language. Right. We can say if F accepts an infinite or accepts infinitely many words, then F accepts some words of length between the number of states and twice the number of states. Right. So to apply this theorem, we're going to look at this. Does this accept a finite or infinite language? So the number of states n is equals to 1, 2, 3, 4, 5. We've got 5. And then we want to find whether or not it accepts anything with 5 letters of that. So we've got A, we've got B, and then once we leave this final state, you realize we are not coming back from this. So since n is equals to 2 and n is equals to 5, and we do not have, there is no word W such that length of W is between than 2n. If L is finite. L is finite. If we had found a word accepted between of length 5, 6, 7, 8, and 9, then we would say that it will be accepting an infinite language. If, for example, this was a final state, this would make a lot of sense. So because we'll be accepting A, B, 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 B. Right? If it accepts this language, then it would mean this was accepting an infinite number of ways. So what is this really all about, right? If you've got how can I put it? If you accept in such a way, it means you've gone through a loop, and the guarantee of you going through that loop means that that loop can be, there's no limit to the loop, it can go for infinity. Any other questions? Right. So now we seem to have a bit of time. We can come back and attempt the question that we skipped. Right, so let's start this and say we want to give the complement of the language. So the complement of each of these languages is going to be, we've got 3 states. We're going to have A. Right, so this is x1, x2, x3. This was an initial state, is now a final state as well. And x2 is also a final state as well. Then for this second one, we're going to have an A, B, with an A, and then over here we've got a B going there. So this was initial, not a final. It's going to be a final state. This is also going to be a final state. This is x2, x1, and x3. Let's call them y. So this is y1, y2, and y3. So we have this now. So now we want to find the complement of. We want to find the complement of one and the complement of the other, right? So let's move down. Right. So we want to find L1 or L2 complement. So that's what you want to find. To find that, we're going to say we're going to have this L1 complement and L2. So we need to grab this. So let me just grab this, pull it down. There we go. Okay, good. So L1, so this is L1 complement. Which one is L1 complement? Is this one and L2. So we're going to draw our table. So we've got new states. We're going to have A and the B. So for union, Z1 is going to represent X1 or Y1. But if you are in X1 and you encounter an A, you go to X2. Y1 and you encounter an A, Y1 you encounter an A, you go to Y2. So this is equivalent to Z2. Z2 is equal to X2, Y2. Then X1 and you encounter B, X1 encounter B, you're going to go to X3. Y1 you encounter B, you go to Y3. So we call it Z3. We're going to have Z3 equivalent to X3, Y3. And then Z2, X2 and you encounter an A, X2 and you encounter an A, you go to X3. Y2 and you encounter an A, Y2 and you encounter an A, you go to Y3. So this will be Z4. So Z4 is okay. Let's see. With an A, you go to Y3. So you go to Z3, not Z4. So X3, Y3, you go to Z3. And then if you're in X2 and you encounter B, you stay in X2. If you are in Y2 and you encounter a B, Y2 and you encounter B, you go to Y1, and this is Z4. So Z4 is equals to X2, Y1. Then if you're in X3 and you encounter an A, you stay in X3. If you are in Y3 and you encounter an A, you stay in Y3. So you stay in Z3. If you're in X3 and you encounter B, you go to X1. If you are in Y3 and you encounter B, you go to Y1. So you go back to Z1. Then if you're in X2 and you encounter an A, X2 and you encounter an A, you go to X3. If you're in Y1 and you encounter an A, you go to Y2, X3, Y2. We did not have this before, so we call that Z5. So Z5 is going to be equivalent to say X3, Y2. Right? And then if you are in X2 and you encounter B, X2 and you encounter B, you go to X3. Y1 and you encounter B, you go to Y3. So this is equivalent to Z3. X3 and you encounter an A, you stay in X3. Y2 and you encounter an A, Y2 and you encounter an A, you go to Y3. So go to Z3. Z3. X3 and you encounter B, you go to X1. Y2 and you encounter a B, you go back to Y1, so you go to Z1. So this is that, and we can no longer we can no longer generate a new state. Let's assign initial and final state. This is an initial state, right? Anything with an X1, X2, or Y3 is a final state. X1 is the final state, X2 final state, Y3 final state, X2 final state, X3, X3 and Y2. This is the only non-final state we have. Right. So this is L1, L2. The complement of this is going to be, right? I'm going to draw the complement in blue. This will be initial, and this will be the only final state. That is going to be the complement. So when we draw this, we're going to say L1 or L2 complement is going to be, we've got an initial state, With an A, you go to Z2, go to Z2. With a B, you go to Z3. Right? Z2 with an A, you go to Z3. Z2 with a B, you go to Z4. Right. Z3 with an A, you go to Z3. With a B, you go to Z1. Z4 with an A, you go to Z5. Go to Z5. With an A, you go to Z5. With a B, you go to Z3. Z5 with an A, you go to Z3. With a B, you go to Z1. With a B, you go to Z1. So here we have got the initial state, and the only other final state is Z5. Like that. So that is L1 in L2 complement. Right? So now you also see that you can then further go and do this one, and because these two are equivalent, L1 and L2 are equivalent, right? So if you want to find the complement, if I take this up, if I move this one, right, we now need to do this one and that one, right? So what we're going to have is going to be the same, more or less the same table. Only difference is going to be the initial and final state. Right? So we're going to have we're going to have this. Definitely, we're going to have the same states that we're dealing with. The only thing that is going to differ is the final state. So Z1 is still going to represent X1 and Y1, right? So the final states that we're going to have, anything that has got X3 and anything that has got X3 and anything that has got Y1 or Y2 become a final state. So the initial state is going to be this one, initial state. And then the final state is going to be anything that has got Y1 or Y2. So here we've got Y2, we've got in X3. So here we've got X3, Y1, Y2. Right. So anything with Y2 is a final state. Anything with Y1 is also a final state. Y3 is not a final state, but since we've got X3, it's a final state. Y2 final state, Y1 is also a final state. Right. So we're going to have this. And then the final state, or when we do the complement, we are not going to have this is X1, XY1, so it's also a final state. So the second part will not have a final state. So the union of these two is going to simply be we're going to have, so we're saying L1 complement or L2 complement is going to be the same, right? Initial with no final state. So then A you go to Z, then B you go to Z3, then A over here, this is B, the B, Z2 to Z4, that will be the B, sorry, the B over here. Then I'm going to have also a A. So we're going to have only an initial state ends and no final state. So we have an A loop over here. So now all that's required is now to find the union of these two. But finding the union of these two is going to be a little bit easy, because what you see is the states are the same. Z1 is going to represent x1, x1. When you go to x2, you go to x2, right? So we are saying L1 or L1, this simply gives us L1. Right? The union of L1 and L1 gives us L1. So the union of these two is going to give us the same, right? The finite automata, the states of the finite automata are the same, the transitions are the same. Only that we now need to find the final state. So this one is the only one with the final state. So the finite automata is going to look like this. The union of these two final states is going to be the union of this one, which is none, and the union of that, which is good one. Right. That understood. Any questions there? Questions? Right. So we stop there for today. I hope to see you again on Thursday when we do the last of our classes and let's wait for the remaining classes. So again, during the period when we're not having classes, if you've attempted a past paper, you can send it through as a whole, and then I can attempt, if you have attempted a question that you're not understanding, send it through to find, then I can respond and send it to you. Yeah, thank you very much for joining us. Enjoy the rest of your evening, and good night.